Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for finding and classifying critical points using the second derivatives test. First, we're going to talk about local and absolute extrema. So first of all, the definition of local maximum or local minimum. A function of two variables has a local maximum, correspondingly local minimum, at a point AB if f of xy is less or equal than f of AB for all the points xy in some disk centered at AB. The number f of AB is called a local maximum value. So the thing that we're saying is at the point AB and in points that are around AB, the function is the greatest at AB. That's a local maximum, and a minimum is exactly the same, but with less or equal instead of greater or equal than. An absolute max is, or an absolute maximum, is exactly the same thing. Now we're saying that f of AB is the greatest value of all the points in the domain of f. So a critical point is going to be of f is going to be when either both partial derivatives exist and the gradient is equal to 0. In other words, both partial derivatives are equal to 0, or if f fails to have one or more partial derivatives at the point AB. So pretty much is when the gradient does not exist. Why the critical points are important? Because in the critical points are going to be the candidates for having local max or local minimum. So the idea is, given a critical point, can we classify, in other words, can we tell whether the function has a local maximum or a local minimum at that point? And the answer is yes, and for that we're going to use concavity. So remember, in functions of one variable, if the function is concave up, then the function has a local minimum. If the function is concave down at the point A, then it has a maximum. When in function of two variables, is going to be three cases. In the case that you have different concavities in two different directions, you are going to have no local extrema. In the case that you have in all the directions concavity upwards, you're going to have a local mean, and if you have in all the directions concavity downwards, you're going to have a local max. So we're going to check how we can check the concavities in all the directions. And for that, we're going to use the directional derivative. Moreover, we're going to use the second directional derivative. The sign of the second directional derivative will describe the concavity of the function at the direction of u. So the directional derivative of the directional derivative is what we are trying to compute. So the thing that we're trying to plug in is, instead of f, we're going to plug in the directional derivative there. And when you take the derivative, the partial derivative with respect to x of the directional derivative, you obtain something like this. And if you take the partial derivative with respect to y of the directional derivative, you find something like that. Multiplying through u1 and u2, this is what you get. Notice that squares are important, because the squares are going to eliminate factors that could influence the sign of the second order directional derivative. So notice that those are always positive. So if you complete the squares and you do some algebra that I'm not going to do here, we obtain this. And notice that in this we have, in this expression, we have that those are always positive. So the only thing that we have to know is, in certain situations, we can analyze the signs of fxx. So in other words, the second order partial derivative with respect to x, and this expression that is in green, that we will see what's the name of those. Notice that in those expressions that I have in color, you don't have the vector u, and that's important, because then we can say that if we obtain that those, the orange expression and the green expressions have certain signs, we can say that the directional derivative is going to be always positive or always negative, no matter what direction we are taking. And that's what we want. We want to determine the concavity in all the directions. So let me tell you about the discriminant of a function. The green number that we have right here, or the green expression, is actually going to be called the discriminant of the function. So one way that you can remember this is to notice that it's actually a determinant, a 2 by 2 determinant, by just taking f of fxx times fyy, that's the first expression, minus fxy times fyx, and but that one, actually they are the same because of Clairaut's theorem, so that gives you an square. So what does this discriminant represent? Well, the sign of the discriminant, you have to believe me of this, describes whether the function has the same concavity in all the directions or not. If the discriminant is positive, then the function has the same concavity in all the directions. If the discriminant is negative, there are two directions in which the function have different concavity. So I suggest you to remember this. This is the key step here. So if you are saying that the directional derivative is negative, automatically we're saying that you don't have a local max or a local mean because you have two different concavities. So let me give you the second derivatives test. The second derivatives test uses this formula in order to describe this. The second derivatives test says that if the discriminant is positive and in the function the second order partial derivative at the point AB is positive, then f of AB has a local minimum. And notice it geometrically is pretty easy to actually remember this. All the directions have the same concavity. That happens when the discriminant is positive, and the second order partial derivative with respect to x both times tells you that the function is concave up. So if all the directions have the same concavity and is concave up in the x direction, is concave up in all the directions, and that's why we have a local mean. The same thing for the other one. All the directions have the same concavity if the discriminant is positive, and if the second order partial derivative with respect to x both times is less than 0, that means that the function is concave down. And if the function is concave down, we have a local maximum because you have concavity down in all the directions. What happens when the discriminant is negative? We remember what we said. The thing that we're saying is two directions have different concavity, so we have that there is no local max or local mean. You may wonder what happens when the discriminant is equal to 0. This test doesn't give you any information. By the way, the point where you don't have when you have a critical point but not a local max or a local mean is called a saddle point. So let me give you an example. So let's try to find and classify the critical points of this function that I have right here. So first we find the critical points of f of xy. In order to do that, we want to find the points when the gradient is equal to 0 and when the gradient does not exist. Since the gradient exists always, we only need to find the points in the domain where both partial derivative with respect to x and the partial derivative with respect to y is equal to 0. So in our case, I'm just saving a little bit of time. I'm taking the partial derivative with respect to x, that gives you equal to that, and the partial derivative with respect to y, that gives you equal to that, and I'm going to set them both equal to 0. So in particular, if I take the second equation, we have that this expression is equal to 0. Since e to the minus x is not equal to 0, then I can divide by that and I obtain that y is equal to 0. Once we have that y is equal to 0, I will plug it in the first equation. So we have this equation over here. After I plug in y, well, first of all, let me divide by e to the minus x. So we have that. But now I'm going to plug that y is equal to 0 in order to have this condition to be satisfied. So that leaves us with x squared minus 2x equal to 0. Factorizing, you have this, and we end up that x is equal to 0 or x is equal to 2. So our critical points is x equal to 0 and y equal to 0, or x is equal to 2 and y equal to 0. So those are the two critical points. So now we're going to use the second derivatives test to actually test each critical point. So the thing that you have to do is you have to compute the second order partial derivatives that are given right here. Believe me, those are the ones. And now the only thing that I'm going to do is I'm going to start plugging in the particular points. So at the point 0, 0, we have that the second order partial derivative with respect to x both times gives you 2. The mixed partial derivatives give you 0. And the partial derivative with respect to y gives you 2, so that gives you that the discriminant is 4. So we have the discriminant is positive, and f of xx is equal, the second order partial derivative with respect to x both times is positive. So remember what happens. I have this switched up. So remember that what we were saying is that the discriminant being positive means that all directions have the same concavity, and f of x, the second derivative with respect to x both times, gives you that the function is concave up. So you have a local meaning. Now let me do the same at the point 0, 2, and this is what we obtain at the point 0, 2. You have that the partial derivative, the second order partial derivative with respect to x both times is equal to this. The mix are equal to 0, and the second order partial derivative with respect to y is equal to 0, and the discriminant, by just doing this easy calculation, is equal to this. Remember, e to the negative 4 is always a positive number, so this is negative number. So now we have that, and finally we're going to get more or less the same situation. So since the discriminant is negative, two directions have different concavity, and if two directions have different concavity, f has a saddle point at 2, 0. So notice that we have two different answers for this. And with this we finish the video tutorial for classifying critical points using the second derivatives test. Thank you.